Hello students, welcome back. We went through all the theoretical details in session 1, but only theory, no practical problem yet. So by now, everybody is dying to get into practical problems so that you can solidify your understanding, and let's go ahead and do that. Here's a nice problem. Answer the following questions regarding the original function f of x, while the graph of its derivative function f prime of x is given below, and also the graph says y equals f prime of x. Find the intervals in which the original function f of x increases and decreases. B. Find the x-coordinates of all critical points of the original function f of x and describe the nature. Local maximum, local minimum, or neither. Let's bundle A and B together as a single problem. And C and D will be about concavities, so let's bundle those together and answer those a bit later. Alright. Now let's look at the graph, and it is tempting to write like this. Decreasing from negative infinity to negative 1, increasing from negative 1 to positive 1.5, and then decreasing from 1.5 to 3, look at my mouse, and increasing from 3 to positive infinity like that. That's the way this blue graph is behaving. But if you do it like this, you just earned automatic 0. That's what we got, automatic 0. Why? Because you just described the increasing decreasing nature of this function. And this blue function is a derivative function. Now the question is about original function, and the problem did not give you the original function. How do you answer this question? Well, remember, the original function is increasing when the derivative is positive, and the original function is decreasing when the derivative is negative. Remember that. And looking at the derivative function here, I can find out when the derivative is positive and when the derivative is negative. Positive when this function is above the x-axis, and negative when this function is below the x-axis. Does it make sense? The derivative is positive when the graph above, which is the graph of the derivative function, is above the x-axis. So around here, the graph is above the x-axis, so derivative is positive. Around here, the derivative is positive. Here, derivative is negative. Likewise, we can say things like this. Derivative is negative when the graph here, because this is a graph of the derivative function, is below the x-axis, down here. But then again, what do you mean by derivative is positive? Derivative is positive means f is increasing. Derivative is negative means f is decreasing. So f is increasing when the graph is above the x-axis. F is decreasing when the graph is below the x-axis. Does it make sense? Because the graph you're looking at is a derivative function. Using these, we can answer this question like this. Let me copy and paste this graph right here. And then let's compare that with this diagram. Because the answer, the most preferred form of the answer in my class will be the diagram. Okay, you can draw a number line, and then please note that this graph hits the x-axis at 3 spots. Right here, x equals to -3, and right here, x equals to 0, and right here, x equals to 3. And those 3 are the x-coordinates of the critical points. That's when the derivative hits 0. Remember, this graph is a derivative function, so y-coordinate is a derivative. So y-coordinate here is 0, right here. X equals to -3, x equals to 0, and x equals to +3. Those 3 are the x-coordinates of the critical points. And these 3 points divide the number line into 4 pieces. Now, in the first interval less than -3, above the x-axis, so derivative is positive, which means the original function is increasing. See the logic? Between -3 and 0, graph is below the x-axis. So the derivative is negative, so the original function is decreasing. You see, I wrote f and f prime there. Can you see the difference there? Okay, maybe it looks a little bit better now. F prime down here, F up there. Oh, let us do color coding. So derivative function is blue, and then the original function is red. Okay, all right, here we go. So the given function here is a derivative function. Blue function is a derivative function. Derivative function is positive here in this interval and negative here in this interval between -3 to 0, and positive again in this interval from 0 to 3, and positive again here greater than 3. So we have plus, minus, plus, plus. And thus, the original function is increasing, decreasing, increasing, increasing. And as for the nature of the critical point, we have increasing to decreasing. That transition takes place at local maximum. Decreasing to increasing, so that transition takes place at local minimum. And finally, increasing, pause, and keeps on increasing. That's neither maximum nor minimum. Make sense? And then you can answer the intervals as, let's see, increasing from -infinity to -3, decreasing from -3 to 0, increasing from 0 to 3, and increasing again from 3 to infinity, or increasing from 0 to positive infinity all the way. You can do various things. And then we have local maximum at x equals to -3, local minimum at x equals to 0, and then the critical point here, x equals to 3, is neither maximum nor minimum. Now, I didn't ask you to sketch the graph of the original function, but you could do it as a matter of fact. You don't really need the graph. Just look at this diagram and you can sketch like this. Follow these arrows. Increasing, hit maximum, and decreasing, hit minimum, increasing, and hit this critical point, and keeps on increasing. So we have local minimum here, neither maximum nor minimum here, local maximum here. Here's a sketch. It doesn't have to be accurate. Let's see, do we have time for one more problem? Okay, here's another problem. Repeat the same problem with the following graph, and okay, we have that. Okay, this time let's do it from the scratch. Okay, we have this number line here, and then we have right here x equals to -2, we have a critical point, x coordinate of the critical point, right here when x equals to 0, and then right here x equals to 4. Doesn't have to be in scale, just ordering makes sense. Okay, and the derivative function, and then the original function. Let's look at the derivative function first. Above the x-axis here, less than -2, so derivative is positive. Now between -2 and 0, below the x-axis, so derivative is negative. Between 0 to 4, positive, and then positive again. You see? The graph hits 0 here and then bounced back up, so staying positive. Therefore, the original function should be increasing here, and then decreasing there, increasing here, and then keeps on increasing. Therefore, we have local maximum here, local minimum here, and then this is neither. That completes the answer as a matter of fact. You could write down all the interval as interval notation. You can also sketch the graph, kind of like this. Like that. Pretty much the same as before. Is there any more problem? Okay, here's a nice one. Do we have enough time though? Okay, I can understand these are asymptotes, so actual 0 takes place only right here at 0. And then the derivative function is always positive. Can you see that? Always above the x-axis. So plus, and then staying positive. So the original function is increasing, and then pause keeps on increasing. So the original function locally behaves kind of like this, like a cubic function. But as a matter of fact, if you look at this part, the derivative gets very, very close to 0, right? The derivative becomes very, very close to 0. So that means the slope is going to become very, very close to 0 as you move to the left and also to the right. So that actually means we are having asymptotic behavior, like this. So we have horizontal asymptote here, horizontal asymptote there, and then I have a critical point that is neither maximum nor minimum here. And then here's another problem. Okay, this one is left to the students. You can do something similarly. You have one critical point here at x equals to -4, another critical point here, x equals to 0, and normal critical point, but we have horizontal asymptote coming down to 0. Good luck.